Hello? Yep. So in the past few days, we talk a lot about the elasticity, which can benefit walking, running, and we use that in the robots, and modeling, lots of things. But now we are going to study on how to choose the stiffness and other parameters which can minimize the cost of the energy. So here's some literature review, and we saw this paper yesterday in Bruce's talk. So they measure the tendon power in walking, and they found that most of the ankle power was contributed by the tendon joint. And another literature review, and they used this working model of elastic ankle foot orthosis, and show that the stiffness can affect the energy cost. So they have the linear spring and the ankle joint, and they change the stiffness. They found this relationship between the energy cost and the stiffness. So here's what we want to study. We want to know how to choose parameters to reduce the energy cost. So we want to know if we change the stiffness and the foot length, how much energy we can, how much energy cost we can reduce. And also, how low the energy cost can go. Can we walk free without any energy cost? And the answer is yes. And the last question we want to study about is active ankle better than passive in terms of energetic cost? So therefore, we have this compliant ankle model. So this model, we have concentrated mass at hip, and we have a linear spring at the ankle joint. This model can walk downhill, and the cost of this model is the heel strike collision energy loss, and which can be compensated by the gravity. And because the most of mass is at the hip joint, so we call this one as the hip power gate. And we fix the walking speed and step length, and we find the link cycle for this model. And this cartoon shows one regular gauge for this model. So in the stem state, our leg move forward, so energy is stored in the spring. And also, the ankle torque will increase as the energy is stored. So when the ankle torque is large enough to lift your heel, we start to return the energy, which helps us to redirect the center of mass and reduce the collision. So here is the animation of this model, just to let you know how it works. So we want to study the effects of the stiffness and foot length on the mechanical cost of transport. And here's our result. We got this contour. So the x-axis is the foot length, y-axis is the spring stiffness. And different color represent different cost of transport. Red means higher cost of transport, and blue is small cost of transport. And as you can see, in this region, it seems like the cost of transport is less. And if we have longer foot with corresponding stiffness, we can decrease our cost of transport. And different region of this contour represent different pattern of gait. So I'm going to tell you about the detail of these patterns. So the first one is this area. We call that no preemptive heel lift gait. So this is the animation, and this is the ankle joint power versus time. So what happens here? For given foot length, if your spring is not stiff enough, and then your ankle torque is not good enough to lift your heel before the heel strike. So the energy returned after the heel strike, which cannot help us to redirect center of mass because the collision has already happened. So the cost becomes pretty high. Another region is here. We call that multi-bounce gate. When we have too stiff spring, so the energy return too early. So before the heel strike, all energy is returned, and our center of mass fall down again, cause some multi-bounce, and the cost is higher. So to minimize the energy cost, we need sufficient elastic energy to redirect center of mass And we also need the energy return in a proper time. So this region is where we can achieve a preemptive heel lift. And when our foot length increase, if we have a proper stiffness which can return energy at a proper timing, we can keep reduce our energy in this direction. So yes, we can achieve a zero energy cost gate. So what happened here is, during the stand phase, we store energy in the spring, and we store enough energy, and then we return before heel strike. So the energy return helps us to redirect our center of mass, and such that the center of mass velocity has already on the path of the leading leg inverted pendulum. Therefore, there's no collision happened when the heel strike, so the cost is zero. And we find this gate when our foot length is longer than half of step length, so it's a pretty long fit. And we found that if our foot length is longer than half of step length, we can always find this zero cost gate if we have a good stiffness. And although we can have this zero cost gate, we believe there's still some trade-off. So here's some example. Because this zero cost gate, we need a longer foot length, and the longer foot causes the double support phase longer, and which requires us to swing our leg faster. And we believe that's one trade-off. Another thing is, if we have longer foot, the moment arm of the ground reaction force about the knee joint is longer, so there will cause more knee extension torque, which should be really uncomfortable to walk with this. So another question we want to study is, can active work enhance the benefit of ankle elasticity? So our model we have a linear spring which is totally passive. So the ankle torque and ankle curve is just a linear line, and this one shows the minimum coastal transport for different foot lengths. And if we look at the ankle torque and ankle curve of human walking, we found that the curve looks like this. And the area inside this curve is the active work done by the ankle joint. So therefore, we change our spring to allow our ankle joint to produce some active work. We call this ankle power gate. So we let this model work on the level ground, not downhill now, and we measure the coastal transport. We found this curve. So for the same foot length, if we have an ankle power gate, the minimum coastal transport can be less than the hip power gate. What happens here? When we have hip power gate, we use the gravity to compensate the collision loss. But the gravity is always directed in the same direction. So that didn't help us to redirect our center of mass. But if we have an ankle power gate, the ankle work can help us to redirect the center of mass, so the collision can be less. So therefore, here is my summary. The ankle elasticity can reduce walking cost by reducing collision, and zero cost gate is possible with appropriate stiffness and foot length. And active ankle power can improve economy with versus hip power by augmenting push-off. And here's the take-home message. Using ankles with power and strength can reduce the gait cost of leg things, whereas hip work makes crash. Ankles redirect mass. But if too stiff, the bouncing mode rings. Thanks.
You mentioned the trade-off between the coastal transport and the foot length, and you also mentioned that the zero coastal transport is possible with proper stiffness and foot length. Have you ever investigated the trade-off between coastal transport and stability?
And
stability, strength of the stability.
Okay, we didn't test light because, well, the stability is always one top thing in this model. So in this model, it's either stable or unstable. So even if we can calculate the eigenvalue, it's hard to say if we have smaller eigenvalue that's better or better stability. So we didn't test that, and because we don't really know how to explain those things.
For example, if we achieve zero cost of transport, then can we make it asymptotically stable?
That's a good question. I didn't check the stability of the whole model, so I'm not really sure about the answer, but I believe it should be stable. Yep. So, sorry? So, what do you mean? Conserved system can be stable. Why is that?
So the zero cost gate has an eigenvalue of 1. So that's the energy conservative part. And then the other eigenvalues don't change that much. I'd say the bigger issue than the eigenvalues is that the zero cost gates are right on the edge where, so in parameter space, they're very close to places where we couldn't find any gates.
Do you have any way of comparing the good ankle stiffnesses and foot lengths that are found in your model, comparing those to human walking and seeing what the similarity is?
Yeah, we didn't do that. Yeah, because this model is still a little bit different from a normal human walking because we don't have a knee ankle, knee joint. So we didn't compare that. But we do have some other study we try to test on the intact subject with the artificial foot with different lengths and stiffness. And we found similar trends, but the mechanics is a little bit different.
What's the right relative distribution of muscle work versus tendon recoil according to your model?
To be honest, I'm not sure the.
Or maybe you haven't checked it yet, but do you have any insights on what?
Yes, we have this the ankle power gauge, and I didn't check the ratio of the power from the spring and the active work. So yeah, I can go back and check, but I don't have the result now.